right, let's get the show on the road. Hello, everyone. Hope you're well. Welcome to another edition of Math 1203. This is our second class. Hopefully you guys are doing okay. Let's actually jump into it. Let me share my screen here. So last time we didn't really do anything by way of the syllabus. We kind of just spoke about the class, how it's going to be run and all that good stuff. So we spoke about mistakes that you should never make. And we looked at the topics list. We know when the tests are going to be and all that good stuff. So nothing much to review there, unless you are new. And I've had some new students register for my class. I'm not sure if there are any in this class, but if you're new, you should definitely watch the first lecture, which by going to the links I'm about to show you, you'd be able to do that and you'll be up to speed. So that being said, let's actually jump into what I want to do for today. And we are going to start with some announcements. Okay. So as I mentioned last time, making sure that I can actually communicate with you is going to be very important for an online class. And so I sent out messages to you guys 4 different ways earlier this week. And I just wanted to make sure that you guys were getting all of those. So it's worth mentioning that again. So here are the links to the class and another shorter link that's easy to remember that you can get to it. So you would be able to access everything from there, the syllabus, the videos, all the class materials. And I just want you to remember that I tried to reach out to you via my Fordham email, Jupyter Ed, Gradescope, and Blackboard. If you did not receive an email from any one of these, then I asked you to email me and let me know. If you were newly registered, then you wouldn't even know to email me. And so really point 4 would apply to you. So if you emailed me letting me know that, oh, you didn't get this communication, I responded to some people, but not to everyone. So I just want you to realize, that it doesn't necessarily mean something is wrong. It's just that because I had an influx of a lot of new students, I just decided, you know what, I'll give it a few days so that I'll just add everyone to the roster and then resend communications then all at once. So just give me a few days to fix this and it'll be fine. If definitely you don't hear from me by Monday, then I probably missed your email, so you should reach out to me by then. But for this week, don't worry about it. You can actually assume that I've received your email. If you have not sent me an email or you're brand new, so you didn't know to send me an email, and you did not get communication from one or several of these options, you should definitely email me and say, oh, I didn't get an email from this or that or whatever. Last time I did the poll, pretty much everyone got an email from my Fordham email address, but not everyone got from Jupyter, Gradescope, and Blackboard. So just make sure that everything is working. And to remind you, I won't be using Blackboard much, but it is important that your Blackboard is working. It could be very important for your other classes. So chances are if your Blackboard isn't working for me, it's probably messed up for the other classes as well. So it's definitely something you want to look into anyway. So in the future, I'm not going to communicate a lot using Blackboard, but you still should make sure that it's working. Okay, one other thing, and this is a little bit more, I guess, personal. I don't know how this class is because I haven't really taught you guys anything yet. But with some of my other class, there is a little issue of shyness going on. And I just wanted to nip that in the bud and be very, very preemptive about that. This is true even in in-person classes. And I did mention some of this yesterday, but it's so much more important for online classes. It's not even funny. So I'm just putting a note here about what I want to say about that. Basically, there's nothing wrong with you as a person if you're a shy person. That is fine. However, you should be aware that there are situations in which being shy puts you at a disadvantage. There are times when you need to speak up. And you have to cultivate the habit that even if you're shy, you are able to speak up when necessary. In class is such a time. It is to your disadvantage if you don't engage in class. So that being said, I know a lot of us have, anxieties about saying something wrong, and everyone's gonna think I'm stupid. This is not true. I don't expect you guys to know everything. It's a class I'm supposed to be teaching you. If you already knew everything, then why are we here, right? So I don't expect you to know all the answers. I will ask some things that I would expect you to sometimes know or figure out, but either way, never be afraid to respond because you're not completely sure. I'd rather you say something like, "Oh, I'm not sure, but I think this would be the answer," or "I'm guessing it's this," or "Oh, it's this." And if you're wrong, it's fine. I'll tell you that you're wrong, but it's not to embarrass you. It's actually to help you. And I'll tell you why you're wrong, and then we can move on. So I can actually replace that. And it's very, very important because as the teacher, it's very important for me to know where your understandings and misunderstandings are, so I know what to address ahead of time. So I don't want you to bring any misunderstandings into the test or the quizzes. So it's best that we clear everything up like right now while I'm here and I can help you. So it's to your benefit. Let's have a conversation. So whenever I ask a question, just chime in. Especially if it sounds a little bit quiet, just say something anyway. At the worst case scenario, chime in and say, "I don't know. I don't know. I don't know," and that is fine as well. I really want to encourage the habit of engaging. It's very important. Okay, so with that being said, let's actually get to. Oh, I had a private message here. I'm not sure, whoever is messaging me, I'm not sure if I saw that email, but if I didn't respond, I will respond after class, okay? So we'll figure something out. Yeah, so let's actually jump into it. Today we're gonna talk about exponentials and logarithms. And I just wanna make sure that you guys are aware of all the mathematical properties that comes along with these. I think most of you would be very comfortable with exponentials. Less comfortable with logarithms, but I would say in general, students tend to not be comfortable with exponentials and logarithms, at least not as comfortable as they are with things like polynomial, right? You start talking about someone y equals x squared, they can draw a picture, they can talk about it, but if you talk to someone about an exponential function or logarithm function, they might know some stuff, they might or may not know how to draw it, they might not even know what it means or what it implies. And that's very common. So I just want to make sure that we understand exponential and logarithm functions. They are very, very, very important, especially in calculus, but important in general. So let's actually jump into that. And this semester, I'll be writing everything out. So it's probably best that I throw in some rule lines here so I don't like write off at an angle. Yeah, so there are sometimes when I pre-type my notes and then I fill in examples in between, but I decided not to do that this semester because I kind of want to slow down the pace a little bit. So I'll be writing out everything that you guys should be taking notes on. All right, so that any questions before we start in terms of the class, or any quick questions before we jump into this? All right, let's do it. Okay, so we're going to start with talking about exponents. Don't remember how to write on this tablet. Exponentials. So what I want you to know about exponentials is, of course, you'll recognize the notation. And I'm not going to explain everything in detail because, like I said, I expect you guys to be somewhat familiar with exponentials. So I'm going to do a real crash course in exponentials here. I'm not explaining everything and why everything is the way it is. I just want to remind you of how things are. So sometimes we write expressions like this, where we write something big and then we write something small to the top right corner. This thing here, that is called the exponent. or power. And of course here of x. The x itself, that guy is called the base. Okay, so the base is x, the exponent is a. Okay, and that's how we write it down. Now, if a is a positive integer, we interpret this as just multiplying x by itself a times. But we can generalize these rules, and so I actually want you to know a more generalized versions of the rules that govern exponentials and how they behave under mathematical operations. So let's actually look at that, the laws of exponentials. So here is law one. If I have two things with the same base and I multiply them, what do we do to the powers? This is where you guys chime in.
Add them.
You add the powers. Right. What about dividing them?
Subtract.
You subtract the powers. Of course, you can't divide by 0, so we're going to assume our x is not 0 in this case. What else do I need to know? What else do I want you guys to know? What if I have something to a power and I raise that to another power?
You multiply the powers.
Exactly. Multiply the powers. What if I have two different things multiplied and then I raise that to a power?
They each get the exponent.
They each get the exponent, right? Powers distribute across products. And at this point, I want to remind you of that blasphemy. Remember, exponents do not distribute across sums. You cannot distribute powers across sums. If your exponent is 1, yeah, but pretty much in all other cases for us, it's not going to be true that it will distribute. So if there was a plus in between the x and the y, then this the analogous thing is not true. Similarly, if it works for multiplication, it will work for division, because division you can think of like multiplying by a reciprocal. So they're very intimately linked. So it will distribute across a division. Of course, we're assuming that the denominator is not 0. Let's get to some, well, let's get a low-hanging fruit. If the exponent is 1, it doesn't change, right? X to the 1 is 1. Something a little more sophisticated, x to the 0, what is that?
1.
It's 1, right? And here we assume that x is not 0. So for us, 0 to the 0 is undefined. We'll actually talk about that later. But the reason is because you can think of x to the 0 as, you know, some number minus itself, which according to the laws of exponents above really means that, which is a number divided by itself, which is 1. So a 0 power kind of has this implicit division going on, and so you can't have the x be 0 for it to work. And there are some other reasons, intuitive reasons, why 0 to the 0 is going to be meaningless to us in some sense, but we will get to that later. What about x to a negative power? What does that do?
Becomes a fraction.
Well, specifically 1 over
1
x to
over-
that power, right? You get the reciprocal. And of course, x cannot be 0 here. 9. What if you have a fractional exponent? What happens now?
It turned it into a radical.
Okay, who gets to be the radical?
The b would become the radical.
Mm-hmm. So this is the radical of b x to the a. We can also interpret this as taking the radical of b and then raised to the a. And for this, we're assuming our x is greater than or equal to 0. We want x greater than or equal to 0 because radicals can cause issues with negative numbers. And for example, the square root of a negative number gives you a complex number. And so we're not dealing with complex analysis, so we're not going to really worry about that case. Whenever we're taking radicals, we're going to either assume that what's under the radical is positive, or we'll specifically state that it won't work for negatives or something like that. Okay. There is a mnemonic to remember this. Mnemonic. It's called flower power. So basically, when you have like x and in the power you have a fraction, you kind of liken that power to a flower. And for the flower, the bottom is the root, which a root is another name for a radical, like a square root, same as radical. And the top is the flower, which rhymes with power. So you'll know that the top number gives you the power of the x. The bottom number gives you the root of the x, right? So those are the laws of exponents. Let's talk about exponential functions. So let's give you the quintessential form. So this is like the generic form. When someone thinks of an exponentials, they'll tend to think of it being like a function that looks like a to the x, where x is the independent variable. Another way to say input, y is the dependent variable. Another way to say that is output. There are other things to call this, but input and output is probably the thing. You'd go with a is a constant. We'll always assume a is positive in this context. Also, some rules will apply to the a greater than 1 case. Yeah. Okay. So that is kind of like an exponential function. Screen is misbehaving. Okay. So we always think of the a as positive, and again, this is because we want to avoid complex numbers. So for example, if our input is a negative number or a something like that, and if our input is like a fraction and our a is a negative number, then if the fraction is a half, we're in trouble because we are taking the square root of a negative number, and then there are all sorts of issues. So we're always going to think of the base as positive to just avoid issues that we don't want to have to deal with. And there are a lot of times when we're just going to assume that the base is larger than 1. And the reasoning for this is that if the base is positive but smaller than 1, we can always rewrite it to something where it is the base is larger than 1. So for example, y equals 2 raised to the x is an exponential. Y equals 1/2 to the x is also an exponential function. However, you should realize that the 1/2 to the x, by the laws of exponents that we talked about earlier, I could actually write that as 2 to the x. So here you'll notice that the base positive, but less than 1. And here I write the same thing, but the base is positive, but greater than 1, right? So when the base is positive, I can write it in an alternate form to make the base greater than 1. And I'll always be able to do this. And so there are some times where I'm going to give you rules, such as when I give you what a generic exponent, the graph looks like, I'm going to be assuming that your A is greater than 1 on these generic graphs. And that's because I can always rewrite it so that this is true. Non-examples. Something like y equals x squared is not an exponential function. In fact, this is someone that we call a polynomial, more specifically a quadratic. It's kind of implicitly assumed that you guys know a lot about polynomials already. So I'm not going to go into that. But this is not an exponential function because the base is the variable and the power is the constant. Whereas for an exponential function, the base is the constant and the power is the variable. And this matters a lot. And do not mix up the two. Of course, note using transformations, and I'm talking about the mathematical meaning of the word transformations. We can generalize this form. So, i.e., something like y equals, so you start out with an exponential, but then you can multiply by some other constant and you can add some other constant or something like that. These are examples of linear transformations. And what it does, it just shifts the graph around. So if I plus c and c is positive, it shifts the picture up. If c is negative, it shifts the picture down. If my b is larger than 1, it'll stretch the picture vertically. Smaller than 1, it'll squish the picture right. So these are still considered exponential. So example, if I have y equals 3 times 2 to the x plus 4, this is still exponential. Okay, so I just want you to remember, transformations still work how you think they work. So let's actually talk about the graphs. Okay, now at this point, I'm just going to tell you just to assume that our base is greater than 1. Remember, because I can always rewrite the graph so that this is true. So, but when we think of the picture, we always think of the pictures where we're assuming the base implicitly is greater than 1. So what does the graph of y equals a to the x look like, assuming my a is larger than 1? It's going to look like that. Where it's passing through 1 here, and we know that by the laws of exponents, when x is 0, you get a to the 0, the output is going to be 1, and goes like that. It always, on the left, it always approaches the x-axis, but it never actually gets there. So we would say that the x-axis, it's asymptotic to the x-axis. I can do y equals a to the minus x. So I can make the power negative. And what does that do? Well, it reflects the graph in the y-axis, right? And this would still go through 1, not drawn to scale, obviously, but that's how it would behave if I made the power negative. So this is a transformation that's called a reflection. What if I have y equals negative ax? So I make the base negative, on the outside, right? So I'm really thinking of negative of the graph, not the A itself is negative, but negative of the whole thing. Then that guy, it flips it upside down. And I could have done both of these at the same time. Negative a to the negative x, and it would flip the other graph upside down. Somehow I always draw the one bigger on the second graph. I don't know why. Jhevon quirk. Okay. So these are 4 pictures you should always have in your mind for when you start to think about what an exponential is. Probably the first thing that should come to your mind is the top left picture, but you should understand if people were to throw in negatives in certain positions, how the graph would behave after doing that. So yeah. And I would think most of us would kind of have seen these guys already. So I'm gonna just move on. If you do have any questions while I'm talking, it's okay to just chime in. Okay. So here is an important fact. And it will become more important to us over time. And I'm going to generalize on this fact later. To include more functions in our comparison. So what I'm going to do is I'm going to compare the exponential function to the polynomial function. So this is just something that you should know about how exponential functions compare in general to polynomial functions. So what I want you to know is that an increasing exponential function grows faster than an increasing polynomial function. Exponentials grow faster than polynomials. And I should probably say any here, just to emphasize that, which I will emphasize a little bit more later what I'm talking about. We can express this by this notation. So I'm going to introduce a notation that I'm going to be using in the future, and I assume you know what I mean by this. So I'm expressing this by saying a to the x is going to be much larger than something like x to the a for any a larger than 1. This basically means as x goes off to infinity and our a is larger than 1. So you'll see me write this expression. And basically what you can interpret this as is a to the x is much larger than x to the a as x goes off to infinity, or x to the a is much smaller than a to the x as x goes off to infinity. This is a fact that we're definitely going to get very comfortable with in this class, but not a lot of people really know what the implications are here. So I want to elaborate on that a little bit. And I'm also talking about this in my finite math business class. And so I really had to get them to understand what the real world implications of what I'm telling you. So this is a fact. It's a mathematical fact. We're going to use it in mathematical computations all the time. However, what does it really mean? Like what you should take away from this? I would like to illustrate that. So let's do a comparison. Okay. So x squared, everyone's favorite polynomial, and 2 to the x, just your generic average exponential example. Okay, we are going to compare these. So let's actually compare the pictures. Let's say I'm going to draw the exponential in red and draw the quadratic in blue. Okay, what does the quadratic look like? Y equals x squared. What does the picture look like?
Parabola that goes to the origin,
What does a parabola look like?
like a U.
Like a U. All right. Okay, so it goes through the origin, goes like a U. Okay, that's that picture. Okay, what does the 2 to the x picture look like? Well, I kind of told you what exponentials look like already. So this guy's going to pass through 1. Right, so those are the pictures. Now, when we focus on the side that is when the functions are increasing, like we zoom over to the left side and really focus on that. If you were to superimpose these guys on, where would they intersect? They'd actually intersect at 2, right? So if I'm looking at these pictures like here, and you can have students who know what both of these graphs look like, and they can sketch it and everything, and so they would look at this and they would say, yeah, I can see how the blue curve and the red curve are behaving differently, but I mean, they're kind of the same, right? I mean, I don't see much difference. They're kind of both looks like the right side of U's, and they're just doing their thing. They're increasing. Okay, yeah, not much difference. Okay, now I want you to realize that this is deceiving. So this is what's called expectation. And not like an official mathematical term, expectation. That's actually a very specific mathematical term in probability. I'm talking about expectation in the meme sense, M-E-M-E, right? So don't look much different as they increase. Which is actually very wrong versus reality. So I want you to really understand how these guys actually compare to each other. Okay, so what I'm going to do now is zoom out. And I'm going to draw the same picture, right? So we're going off to infinity, right? So a bajillion, gazillion, and whatever other made up word you want. Okay, so here, come on. Let's draw my 2 to the x. I know it's going to look like this. Okay, so that's my 2 to the x. All right. What would the x squared look like on this picture?
The U would be a lot thinner. It'd be closer to the sides would be closer to the y-axis.
You mean it will look like here?
Yeah.
Nice guess, but no. It'll be the opposite way. It'll actually be closer to the x-axis. But here's what is actually surprising. If you zoom out far enough, here's how it's going to look. It is still U-shaped. However, compared to the exponential, it's like it's not even trying. It's increasing, but it's effectively not doing anything. The exponential increases so much faster than the polynomial, to the point where if you zoom out far enough, it's like the polynomial might as well not even try. Why did it wake up this morning? Like, it's not, you're not in the game. You're not, you are not, me and you are not the same, right? They're not the same thing at all. right? So it turns out, so the x squared is effectively 0 compared to 2 to the x when x is large, right? It's literally like it might as well be nothing. Like on a large enough scale, the difference between x squared and 0 and an exponential function, I wouldn't be able to tell the difference between x squared and 0. Like it's really mind-boggling. When I say that an exponential grows faster than a polynomial, I really want to emphasize that I'm not talking about, oh, it's a little faster and oh, they're kind of the same, but the exponential is going to be steeper eventually. And no, I'm meaning there is no contest. Okay. And this is something that a lot of students actually misunderstand. This is an example of one of those things where, you know, a lot of people go through math classes and they're like, I never used math in my life. It's pointless. What is this good for? Why do we need to know this? So they would learn something like this mathematical fact right here, and they'll be able to use it in computations and do stuff, but they don't really understand what it means. And so what happens is in the real world, we have all these things that seem really crazy and mind-boggling. Everyone's like, how did that happen? That doesn't make any sense. And the reason is a lot of the times it's because it's an exponential and people don't really understand what that means. And it's also kind of built into our nature because human beings psychologically, we're very good at conceptualizing things that grow linearly or like straight lines, which is an exponential with power 1. We're very good at doing that. Like we're good at predicting things that move linearly. However, you'll notice that in the short term, we're not going to notice much difference between a polynomial and an exponential. I mean, even if I look at the line y equals x at this point, the white line still might not look like it's doing anything much different. And of course, human beings are very impatient, so we're not going to stick around forever to see what the difference is. We're just going to be like, well, in the short term, I'm looking at it, not much difference. So yeah. And what happens is we start to think of everything almost as linear because it's very easy conceptualization that would happen. And so our intuition works very well with linear. However, it turns out exponential things are a lot different. And in the short term, they would seem very similar. Seem similar in the short term. But as you move out, the similarities quickly begin to decrease. And this is why you can have all these weird situations like, you ever notice how the ultra rich just keeps getting ultra richer? So you can have this, you know, a multi-billionaire, and they'll give away millions of dollars of their fortune. They'll get into philanthropy and they'll give away millions, billions of dollars. And yet somehow the following year, their net worth is even higher than it was the previous year. And everyone looks at that like, dude, how are these people just getting very rich and so rich? And, you know, and then we start talking about, you know, wealth inequalities and all that sort of thing. And to be fair, there is a wealth inequality. I'm not denying that. But the reasons aren't what we might think. And it's not as straightforward as what we might think. And because for the average person, you know, if they splurge 1 month, then, you know, they're in trouble for rent the following month. They can't understand how someone with billions of dollars can give away millions of dollars and be better the next month. And that's because typically the average person's money grows like a polynomial, grows pretty linear, while the average billionaire's money grows like an exponential. They tend to be invested in more lucrative things that gets their money compounded over time. Compound interest transforms the growth of your money into an exponential function versus a linear function. And so, you know, the guy that saves $100 every month under his mattress versus the guy that puts $100 every month in a bank account that earns, well, it won't be a bank account. No one's going to give you this. That earns 4% interest over time. In the short term, these two guys are going to not seem very different. When they retire, though, the difference between these two are going to be very different. One of them is going to be a millionaire. The other one is not even going to be close. And so in the short term, you don't notice the difference, but over time, it becomes glaringly different. You're not going to notice in the first year, the second year, the fifth year, but after 30 years, 40 years, you're going to notice a lot of difference. And even in the short term, let's say we had someone who had their money invested in 4%, but they had a net worth that's more similar to the average person. Then yeah, if they splurge 1 month, they're in trouble the next month. However, if they were able to accumulate a lot of wealth, so they're starting out here, then they can give away a lot and drop down here, but then they'll still get higher even faster the next time. And that's because things are growing exponentially. So, you know, you'll have things like this. So it turns out that a lot of the decisions you want to make, so a lot of times people make decisions in life like where to put my money. I think saving in a checking account is okay. It's not. The math says it's a bad idea. You're effectively not growing anything. In fact, because of the existence of inflation, you're actually losing money by saving in a checking account. The person who really understands the exponential function knows it's safer to put their money at a little bit of risk where it can gain compound interest, right? So these are some of the intuitive things that aren't really stressed in math class, but I thought I would just bring that out. I really want you to understand what these rules are saying in the background, what they imply, what they really mean. Because in a typical class, that's how everyone thinks about it. But it's the truth is far from that. These two things are not the same, not even close. All right, so I do want you to fully appreciate that. Exponentials grow faster than polynomials. Faster, all caps, bolded, 20 size font, double underline, okay? So that's a very important thing to know. Now, here's another important fact. There's an important type of exponential function. So there's one very specific exponential function that we really like, especially in calculus, but in general. This is the function that looks like e to the x. And I do want you to appreciate here that because it's an exponential, e actually represents a constant. So yes, I know I wrote a letter, but it's really a constant, right? E is like pi, right? It's a constant. We just have another symbol to represent that number. So e is a constant. It's roughly 2.71828, and it's a non-repeating decimal. So it's an irrational number. So the digits, to someone who doesn't really understand what's going on, just appear at random after a while, right? So it's actually a number. This is called the natural exponential. Okay. That's what we call it, the natural exponential. E is called the natural number. And no, not the natural number. E is called Euler's number or Euler's constant. Right, the E comes from the first part of Euler's name. Pronounced Euler, not Euler, like a lot of people. It's a Swiss mathematician, so it's pronounced Euler. It's named after this guy who was investigating, of all things, compound interest. The idea is the following. Say if $1 was invested in an account gaining 100% interest compounded continuously, meaning you add interest an infinite number of times. So you keep adding the interest back to the dollar an infinite number of times over some time period, over 1 year. What would be the balance in the account at the end of the year? Right? So a lot of people listen to this question, and especially if they understand how exponentials work and they understand how things like credit card debt work. This is why a lot of people get in trouble with credit card debt because they're not paying attention. Because again, conceptually, they think like their debt, when the credit card company is adding to their debt, they envision it being linear. And eventually, in the short term, the extra money that your institution is charging you to have debt on your credit card doesn't seem like a lot of money, but over time it gets out of hand, and before you realize it, you're in trouble with credit card debt, and you're worried about, you have to find ways to get out of debt. And that's because the credit card debt grows exponentially, whereas most people's bank accounts grow linearly. You might be able to keep up in the short term, but if you let it go, you get in trouble, right? And a lot of people know this, and they're like, my credit card is charging me 20% compounded once per day. What would it mean to compound 100% an infinite number of times per day? What would happen to this $1? I'd have an infinite amount of money at the end of 1 year. It turns out that's not true. The answer is you would have $E at the end of 1 year. You'll have roughly $2.72. And Euler was one of the first guys to figure this out. And that's why it's called Euler's number. You'd have roughly $2.718 over this year, right? So he figured this out. He knew how to compute it to a very big precision, a very high precision. And so we named it after Euler. A lot of things are named after Euler. He's one of the most prolific mathematicians in history. Yeah, so I want you to be aware of that. And there are many notable mathematicians consider y equals e to the x to be the most important function in all of math. It's for sure, it's the most important function in calculus. Not everyone would stretch it beyond that, but there are a lot of people who think like the natural exponential function is the most important function ever. We get so many things from it, and you'll see this a little bit later. I might derive some things for you. You'll realize a lot of the rules that come from calculus, we actually develop them by using the exponential function. I won't always do this. Sometimes I'll just tell you the rule, but there are a lot of rules that I tell you, like you said, how did someone figure that out? They actually use the exponential function. So it's very, very, it's an important example of a function. So what we're already a little bit out of time, but I just want to state some, the other kind of function that we want to look at and some rules. Logarithms. I'm not really going to ask you guys to chime in here because, I tend to expect people to know a lot less than logarithms, and I just want to get us out of here as soon as possible. Definition. A logarithm is an exponent. In other words, more specifically, the logarithm of a number to a given base is the power or exponent that we must raise that base to get the number. The notation looks like this. We can say logarithm, and we have our little base down here, and we have the number right here. And what that is, it is the power that we have to raise the base to get the number, right? So that leaves us with this notation. This is called log to the base a of b. And the definition tells us the rules. So here's the first rule, which is literally the definition. So it's a very important rule. It basically says that if log to the base a of b is c, it means that if I take a raised to the c, I get b, right? The exponential equation with e raised to the power c equals b, a lot of us understand conceptually what that means. You can actually rewrite this in another way to get the log, to get c, solve for c as the power, and to do this, you get a logarithm. And it turns out that this definition brings with it a lot of other nice rules, and I'm just going to write them down and then let you go. So here's a second thing. If I have log to the base a of something raised to a power, that is the same as I can take the power down and multiply the log. If I have log to the base a of something times something else, I can write this as a sum of logs. If I have the logarithm of something divided by something, I can write this as a subtraction of logs. And I want you to appreciate the analogy here of how this is corresponding to our laws of exponents. We know that when we multiply things of the same base, we add the powers. When we divide things of the same base, we subtract the powers. This is why it's connected by addition and subtraction when we're multiplying and dividing. 5, this is called the change of base formula. And I'll talk more about this next time. It allows us to change the base of the logarithm. So if I have log to the base a of b, I can write that as log to the base c of b divided by log to the base c of a, where c is a convenient base. And I'll talk about why this formula is important later, but oftentimes we use it to transform things to base e because it's very nice to work with e in calculus. So I would say the following, you must memorize the above. You must know these first 5 rules by heart as well as you know your name. Optional, but highly recommended that you remember a few more things. Let me emphasize highly recommended. Your life will be very hard if you don't. You also memorize these other rules that I'm going to give you. So, law 6. Log to the base a of 1. Log of 1, what is that? It's always 0. Why? Because if I take a raised to the power 0, I get 1. We know that by an exponential rule. 7. Log to the base a of 0 equals, what is that? Well, turns out it's nothing. It's undefined. Why? If I have a positive number, there's nothing I can raise it to get 0 as an output. If it's 2 and I keep raising it to a power, it will never become 0. In fact, log to the base a of x is undefined if x is negative. Again, if I have a positive base, there's no power I can raise it to get a negative base, right? Negative in the exponent just puts 1 over the thing. 8. If I have log to the base a of a to the x, well, that's just equal to x. Why? I have to raise a to the x in order to get a to the x, right? So as long as it's defined. This one is a little less intuitive, but it's also true. If I have the exponent and I raise it to log to the base a of something, I also get the something. And lastly, and this is not really a rule, it's more of a notation. We write ln to mean log to the base a. So whenever you see me write ln, it's a logarithm, and it just, not base a, base e. That same number I spoke about earlier, right? So this is a log called the natural log because it has the base of the natural exponential. It obeys all log rules. So we think of it as special, and for a very good reason, but it's not special in the sense of its properties, meaning if I take ln of something times something, I still can take ln, that means ln of the sum, right, etc. Right, and if I were to say something like e to the x equals y, it's the same as saying that ln of y equals x, right? So all the log rules will apply to the natural log. I'm going to give some examples about the change of base formula and talk a little bit more about logs next time, but for now we will stop there. And as always, I will post the notes here of all these rules, but essentially these are the log rules. Students tend to be less familiar with them. You must know the first 5 rules by heart. I highly recommend that you learn the next 5 rules. And if you actually study a lot and practice a lot of problems, you'll actually automatically memorize the last 5 rules without even trying to do it. But yeah, we will stop there. We will pick up on Friday. Any quick questions before we depart? Okay, all right, so we will stop there. Thank you for your attention. I'll see you guys in the next one. Ciao.